So thank you all. So my name is Brooks Hanson. I'm the Executive Vice President for Science at AGU, and I'd like to welcome you all to this great session featuring our Mcilwain and a few other award winners. The convener is myself, Endoy Yazagai, who's part of the African Award Committee, Julio Betancourt, part of the Mcilwain Committee, and Denis Didier Rousseau, who I can't, there he is, who's our fall meeting program chair, helped put this session together. And this has been a little bit of an evolution over previous sessions where we simply asked our Mcilwain winners and other award winners to give a scientific talk. And we appreciate them stepping up to the challenge this year. But we thought it'd be really interesting to get some of our next generation scientific leaders together to imagine as we start our centennial this year, well, next year, but we're starting it this year at this meeting, to kind of help us imagine what some of the future challenges in the science and the earth and space sciences and sciences are and how we might address them. So that's how this session came together, and we really look forward to the discussion. So to still maintain some part of that previous model, but move into this new model, what we're going to ask, the way this is going to work is, I'll turn this over to Julio in a second to introduce each winner in turn, and then they will have 5 minutes to tell us the highlights of their science as they see it, and then we'll call them all up for a vigorous hour-plus panel discussion on where our science is going and how we're going to get there. So we're really looking forward to a great discussion, and thank you all for participating in this and stepping up on our centennial celebration. So thank you. So let me turn this over to Julio, and welcome again. Thank you very much.
Thank you, Brooks. I was just mentioning to Brooks that he was the editor on my first science paper. It was downhill from there. Yeah, didn't reject it. Had great comments. So this new generation of scientists session, in part, is to honor our 5 Mcilwain Medal Award winners and our African Award winners for research excellence in the earth sciences and in the space sciences. And then there was another awards solution in science. And I want the audience to congratulate everybody. These are amazing awards. I've actually served as the chair of the Mcilwain committee for the last Mcilwain round, and I've been on the committee for 4 years. And so I've watched this parade of excellence. That's been so impressive. I think Brooks probably knows this, but one of the things that I notice, at least about the Mcilwain winners, is the frequency with which you're actually cited for excellence in refereeing, which is really unusual when you look at lots and lots of CVs like I do. So congratulations. So what we'll try to do is, we're already running a little bit late, but try to get through the 5-minute talks. And then we'll move to the discussion. And we sent a list of questions prior to the meeting that hopefully people have had a little bit of time to think about. And I'll restate the questions at the beginning of the panel discussion. So the stairs are over there. Drew, you want to?
Thanks, Julio and Brooks. So I will keep this quick, I promise. My main point is already right there in the title, and it's, for those of you that don't know me, I study space plasmas. And we're very lucky with Earth and near-Earth space because we can study some very fundamental physics in this beautiful natural laboratory. One thing that a lot of people tend to not realize is that space is not empty. It's full of plasma. And one of the problems is that it's just not visible, right? However, some of the places where it is visible, such as the sun itself or our upper atmosphere, displays to us just the beautiful, beautiful complexity that we do have with these plasmas in these systems. And looking out, plasmas are quite important to us in general. So the physics that we're studying are applicable to a wide range of pretty important realms. Some examples here, if you think about laboratory plasmas, the fundamental instabilities in a plasma are one of the, if not the, major reason why we can't get cold fusion to work well. These laboratory devices where we're trying to achieve this are plagued by instabilities within the plasma itself. And those physics are some of the same things that we're studying when we look in space. Another one is, of course, the space environment itself around the Earth and where we send our astronauts as well as any satellites into. From a space weather perspective, that environment is not benign. There are some particularly nasty zones, such as the radiation belts, that we need to understand. It's important both to protect our astronauts as well as our assets in space. And then, of course, astrophysical plasmas. I've got this nice image here from the science. It's from Science Communications. And that's showing probably, I guess, a black hole there in the middle and the beam that you're getting coming out of that. And, of course, the accretion disk around as well. So really nice artist rendition here. But the key thing there is that's also plasma, right? And the universe from an astrophysical standpoint is mostly plasma. So ending here, again, the main point is just that with our heliosphere, so you'll hear heliophysics, it's one of the divisions of NASA, and what we're studying in heliophysics is really advantageous from a broad perspective across a wide range of fields, all of which plasma physics are critical to. And we have this incredible natural laboratory right around us in space to study these processes. And I'm just going to say a quick shout out with the last couple minutes here to some of the more recent NASA missions that we've been using to study some of these physics. Looking at, say, particle acceleration in magnetic bottles and at collisionless shocks, we've had some very recent success understanding this with NASA's Themis mission, the Van Allen probes, and MMS, ESA with the cluster mission, and now JAXA as well, the Japanese Space Agency, with their RSA or ERG mission. And CubeSats, which I've got here as well as down there in the future missions, they've also been proving themselves more and more valuable. Magnetic reconnection, that's one of those things that really is keeping us from getting that fusion working well. We've been studying that now with the MMS and Themis missions as well as cluster. And finally, looking forward, sticking with the theme here, we have another big NASA mission coming up, interstellar mapping and acceleration probe, IMAP. But as well, and one of the things I really wanted to stress here with the last 30 seconds is just these CubeSats, these small satellites, and the multi-point capability that we can get with those. That's one of the things I would like to stress is something that looking forward to the future, having that multi-point capability is going to be critical because of the complexity in these systems. You know, these pinpoints that we get with a single satellite just aren't enough anymore. We need multiple pinpoints to start putting the full picture together. And I'll leave it there.
Great job. Thanks. Caroline? It's Caroline Ummenhofer from Woods Hole. Yeah, there it is right there.
And where's the mouse that I can use?
I'm sorry?
Where's the mouse that I can use?
There is a mouse, and you'll have to move your.
Okay.
Here, we can take it and put it up here.
Okay, great.
All right.
Okay, so good afternoon, everyone. I'm an oceanographer and climate scientist looking at extreme hydroclimatic events on land and the ocean's role in particular in driving its impacts on the human and natural system. So robust evidence exists that certain extreme weather and climate events have become more common and have changed in regard to intensity and frequency. And so pictures like the one that you see there on the right that highlights unusual climatic conditions all over the world, this is just one particular year, 2010, are becoming more and more frequent, and you see that pretty much no area around the world doesn't experience unusual conditions. And so our confidence in detecting and attributing, so that means associating any particular climatic event with a specific cause, really varies by different types of events. So we have much better confidence in temperature extremes than, say, rainfall extremes. Specific event characteristics like duration or intensity for a heat wave, for example, or also on the quality and length of the data record that is available. Extreme events by definition are rare, so we only have a very short record for most regions, and so there are regional variations in how confident we are with certain extreme events. Event attribution, so associating one particular extreme event with its specific cause, is most skillful when three ingredients are met. One is we have a very good understanding of the physical processes that drive that particular event. Second, we have long-term records that allow us to place the event in a longer record and actually identify this. And then third, we have numerical simulations that allow us to replicate the event and also allow us to replicate it for the right reasons. In a recent review article in the Philosophical Transactions of the Royal Society, we reviewed some of the challenges and opportunities that exist, in particular in understanding extreme climatic events and their impacts on biological systems. So especially when you're looking at biological systems, we already have a fairly short record for climatic events and the physical climate system, but even more so for the biological system. Our record and good quality length of records is pretty limited in regard to depth, and with depth I mean time dimension, and breadth, spatial scales, as in global scales or across regional scales. And there's a mismatch between the biological system and at what spatial and temporal scale that experiences extreme events, and at what scales we can represent those. So, apart from these challenges, there's also considerable opportunities that exist at the moment, and that make this a really exciting field to be in. There have been recent advances in event attribution. There are improved spatial resolution of both climate models and statistical and dynamical downscaling. Continued development of Earth system models with biogeochemical cycles that allow interactions between the biosphere and the physical system, and also in particular technological advances in observing the system, both the physical climate system as well as the biological system. And so in my last minute or so, I'd like to give you one example how the ocean in particular affects hydroclimatic extremes on land. Shown here is a map of Australia, which experienced its wettest spring in 2010-11, and many regions across Australia experienced 400% of their annual rainfall, associated with devastating floods in much of the northeast of the continent. Australia generally makes news more with droughts, but this was one year where it really experienced very severe flooding. And there was so much water dumped onto Australia, essentially, that you had a drop in global sea level, as you can see down here in this figure, where 2010-11 really stands out as a drop in the mean sea level anomaly. And that has to do with the unique situation in the interior of the Australian continent. So shown here are water mass storage from remote sensing satellites that show that Australia contains so much water in the surface layers for sustained periods of time, months at a time, that you could see this drop in sea level. And that has to do with the interior of the Australian continent, the Lake Eyre Basin, which is normally a salt-crusted playa surfaces. That is one of the largest internally draining lake systems, 9 to 15 meters below sea level. And when it is filled, which only happens very rarely, once every 20, 30 years, it's one of the top 20 lakes in the world. And that removes that water in that internally draining lake system from the hydrological cycle. Now, one could question what caused this particular event in Australia during 2010 and 11. And shown here are the sea surface temperatures, ocean temperatures around Australia in the Indo-Pacific. It was a very strong La Nina event that normally leads to a lot of rainfall in Australia, but also record temperatures very much enhanced so around much of the Australian continent. And so we know that ocean temperatures have been warming over the last decades. And so the question we wanted to ask is, what role did the natural variability, the La Nina event, play, and what role did ocean temperatures play? Now, you can't tease that apart in reality, but you can in a model. And so we went to an atmospheric model where we put in sea surface temperatures exactly as they were during 2010-11, and one where we removed the trend, and then ran the model, not just once or twice, but 100 times, and got a distribution of rainfall across Australia or the northeast of Australia. And so you can see here, compared to a control in black, no matter what, 2010-11 would have been pretty wet, or you're enhancing your likelihood of having wet conditions. However, that it was as wet as observed or wetter was significantly enhanced in this red distribution, which has the additional ocean warming. So the ocean skewed the chances of having this much or more rainfall in 2010. So to summarize, the ocean's role is really important for hydroclimatic extremes on land, but I'd also like to give another shout out to the ocean in this regard, because most of our understanding about extreme climatic events is from the terrestrial atmospheric realm. That makes sense because that is where we live, that is what we experience, where we have data. However, there's a growing recognition that the ocean also experiences extreme events, like marine heat waves, for example. And so in that sense, the new modeling and observational capabilities can give us new tools and resources now to actually work on both terrestrial and marine environments and extreme events. And it's an exciting time to be working on this. Thank you.
Isaac Santos from Southern Cross University in Coffs Harbour, Australia.
All right, so my talk is going to be about linkages between hydrology, oceanography, and biogeochemistry. So much of the work I do is at the interface of those disciplines. I find it hard to identify myself with any of those because I tend to float between those disciplines. Can I borrow this one? Yeah. All right. Okay, so I'll be talking about mangroves. But we can imagine that mangroves, in a way, they represent many of the coastal ecosystems like salt marshes, seagrass beds, coral reefs. So many of the problems I'm going to talk about actually apply to many of those other systems. So when you think about carbon sequestration, the community started by looking into how much carbon trees take up from the atmosphere. right? So that's primary productivity. And then we soon realized that much of that carbon ends up in the soils, and the soils store large amounts of carbon. So here you can see some data of carbon stocks across a latitudinal gradient in Australia. We have about 1 order of magnitude more carbon in the soils than in the biomass. So carbon is hiding the soils. With that, the community started trying to quantify the rates, how fast that carbon is accumulating there. And then we started calling that blue carbon, the carbon that those coastal vegetated ecosystems sequester on long time scales. Mangroves are very good at that, at sucking up carbon from the atmosphere and putting in the soils. So my question has been, what's the fate of that carbon? Where is that going to? Because carbon is usually organic, people tend to focus on organic components of the carbon cycle, like DLC, or dissolved organic carbon, or POC, organic particles. What we're missing here of the big components is DIC, dissolved inorganic carbon, which is mostly bicarbonate in groundwater. So that's a bit of the focus of my research. I'm looking for that DIC. How much? Where is that going to? What happens along the way? So the way I approach the problem is by essentially using technology that others have developed. I put them together in a big package, and we can resolve the whole carbon cycle using automated, high-precision observations. So with this type of technique, we can get lots of data very quick at very high resolution, and we can look at detail changes over time and space. So what we have been trying to do is to build a whole system budgets and incorporating some hidden hydrological pathways like submarine groundwater discharge. So we have those budgets for many systems now in Australia, Indonesia, China, and they're building those things. So that's an example. So rather than just looking at the primary productivity or the bearing the soils, we're trying to look at what's coming out of the soils for all the key carbon species. And what you see is that the carbon that comes out of the soils that gets into a near shore waterway, and eventually that travels to the ocean. And we have outwelling, which is a hypothesis that has been going on for decades. That outwelling from marshes supplies nutrients and carbon to coastal ecosystems. So we're trying to refine an old hypothesis by incorporating inorganic carbon or bicarbonates. And what you can see here is that the numbers for DIC, they can be quite high. So we have lots of inorganic carbon coming out of those soils. And this number, 26,000, is about 5 or 4 times bigger than soil carbon burial. So the blue carbon community has been looking at the soils for answers to carbon sequestration. And I think by just looking at the ocean as an oceanographer, we start finding lots of the carbon that was just essentially invisible. There is so much bicarbonate in the ocean that that little addition is very hard to actually find. So we are now building those data sets for a number of those systems. If you believe in extrapolations, that's the basis for the extrapolations I'm going to show you. We have lots of data from Australia, a bit from Asia and the Americas, not much from Africa. So when people were building carbon budgets 5 or 10 years ago, we had this big pie of a big slice of unaccounted for carbon. And what you're finding now is that DIC is a big chunk of that pie. So the alkalinity or bicarbonate exports, they are twice as big as DLC, the organic carbon exports, or the carbon burial. That's our definition of blue carbon. When that bicarbonate goes to the ocean, it can actually buffer the ocean against ocean acidification. So the pH can go up on a localized scale. And on a global scale, it can give us more blue carbon or more carbon sequestration than we would have only by looking at the burial. So by looking at seawater chemistry, we're actually giving more credit to those valuable coastal ecosystems. stop here. Thanks so much.
Walt? So this is Walter Immerziel from the University of Utrecht, Netherlands. Thank you.
Thank you. So, yeah, the title of my presentation is From Snowflake to River Basin, a multi-scale exploration of Asia's water tower. And that basically also sums up what I see as one of the main challenges that we have in the next decade. How can we make, or how can we bridge that huge scale gap that we have from understanding fundamental processes in the high altitude water cycle to really understanding a very large region? So what I do in this talk is I will not give you a big science talk, but I have put together 4 points which I think are going to happen in the next 10 years and which will hopefully change our field to the good. I first want to introduce a little bit the region that I'm working in. This is what we in general call High Mountain Asia. So it's a very large area and it contains many mountain ranges. You see them here summed up. So we have the Himalayas, which most people think about, but there are many other mountain ranges in Asia, such as the Karakoram, the Hindu Kush, the Pamir. So all of that together we call High Mountain Asia. And in this region we have, it's so fascinating because we have tremendous climatic contrast. So if you look, for example, in Bangladesh, which is very strongly dominated by the monsoon, we have the wettest spot on Earth there. It's in the Meghalaya Hills and there's about 12 meters of annual rainfall. But then if we cross the Himalayas and we go to the Tibetan Plateau, we have mountain deserts there where we have 200 to 300 millimeters of annual rainfall. We also have the largest areas of glaciers here outside the polar region. So in total it's about 100,000 square kilometers of glacier areas here. It's also a region that is very inaccessible, so it's very difficult in general to do fieldwork there and to do actual measurements on the ground. And in addition, there's a lot of geopolitical tension, so there's also issues related to security and conflicts between countries. In this area, we also have the world's largest irrigation systems. So we have, for example, the Indus Basin irrigation system, which is the largest continuous system that exists on Earth. And if we add up all the people that live in those river basins, which have their headwaters in the Himalayas, it's about 25% of the global population. So at the same time, climate change is impacting the mountains pretty hard. And also the socio-economic developments here are very strong. So populations are growing very quickly, diets are changing, and people are getting richer quickly. So all of that together makes this a very fascinating area to look at. So the first thing that I think will happen in the next 10 years is that the scale gap that we have, that will be bridged through cloud computing platforms. So if we go into the biggest zoom, that is our research catchment Langtang, which is about here, and we just measure there already for a number of years, for example, a single glacier. But the complete picture is, of course, much more complicated. How can we say something about the climate change response on a big river basin? So how can we upscale this? And I think with developments like Google Earth Engine, high performance computing, more and more high resolution models, I think in the next 10 years big leaps will be made in overcoming this scale gap. The second thing I think that is going to happen is that drone and sensor developments will change the way we observe the cryo and hydrosphere. We have been, I think, one of the first who have been using drones on glaciers in High Mountain Asia. And you can see here on this visualization that the amount of detail, this is actually based on our drone data, is really impressive. And up till now, we have mostly used optical cameras, but I think more and more sensors can be deployed on drones. And I think it will be only a matter of time that we can, for example, measure a full energy balance using drones. In addition to drones, there are also, for example, in the weather stations, we see more and more small stations being developed at relatively low cost, and we can put high densities of these stations everywhere where we want, and the data is automatically transmitted to our computers back at home. The third thing I think where we will see a lot of developments is that daily high-resolution satellite imagery will lead to improved understanding of cryosphere dynamics. So Drew already mentioned CubeSats. We are also using them very frequently. You have, for example, the planet constellation of satellites, and for example, in our region you have now a daily coverage of about, let's say, every 5 days you have an image at a resolution of a few meters. So that is a very nice development. On the left you see, this is based on a study we published last year, and there you see a surging glacier. So this glacier was moving forward very rapidly within a period of 3 months, and huge amounts of mass were transported from the higher parts to the lower parts, and it blocked the river. And without those planet satellites, we could never have identified this process or modeled it in so much detail. The last point that I want to make is that I think that machine learning and big data will lead to new discoveries and connect mountain disciplines. I don't think machine learning will actually replace our process-based modeling that we are doing, but I think the combination can be quite powerful. So machine learning can be used to identify connections that we don't know yet, and then we can use process-based models to really unravel the mechanisms. So to conclude my presentation, and I'd like to quote Alan Robock here, and this is also very true for the mountains. It's real, it's us, it's bad, we're sure, and there's hope. And I think with those new technologies, we will see lots of development in the next decade. And with that, I think I'm ready, and I thank you.
Stephen Davis from UC Irvine. Might take us a minute to get this back.
Yeah. No, the next one.
All right, thanks, Julio. So unlike some of the talks you've heard so far, my research isn't just relevant to human activities, but it usually involves some analysis explicitly of those activities. So the reason I start with that is that a lot of the same things that you heard of from my colleagues, the technologies that they listed, that is, which it's interesting how many of us have mentioned some of the same things. But these technologies are going to change not just the science for me, but also what it is that I'm trying to study. So, for instance, trends in automation, autonomous vehicles, the rising dominance of renewable energy sources that may be facilitated through different chemistries of batteries and electrolysis. But things like the big data that came up in a few other folks' talks and the algorithms and computing power to make sense of that, that might not just help with my research, but it may actually have an impact on some of the systems that I'm studying. So that's kind of interesting. That said, I'm going to sort of dodge the question that you see at the title here that the conveners asked us to answer and make maybe a little bit of a provocative argument that, in my view, the science in coupled human and natural systems is not going to jump by leaps and bounds because we get breakthroughs in data, for instance. I imagine in 10 years, every one of us here is still going to be asking for more data. That's never going to change. It's a perennial problem. The science is going to take a big step forward despite this lack of data, and it's really the scientists who come up with clever angles to analyze the systems despite whatever lack of methods or data they may have that make big bounds or leaps. So I think, as I just said, the breakthroughs that will matter most are going to test the limits of whatever data we do have available, and in my view, it's much more about asking the right questions and finding clever ways to address those things. I heard a lecture recently that was recorded by Richard Hamming, a famous computer scientist, and he talked about how great scientists walk around with maybe 10 or 20 problems in their head at all times. And no matter where they go, and if they see someone else giving a talk or they're wandering in the poster hall here, they're looking at those posters or hearing the talks and reflecting on how could this method be applicable to one of those problems that I care about. And I really think that that's true. So in sort of response to that, I've thought about, well, what makes a good question? And I don't think it's strictly that the answer to the question has a big consequence for people. I think it also really matters that you have some novel approach to getting at that question. So you need both of those things. So here is a few bullets just opening the kimono a bit of questions that I've been carrying around in my head lately. And the laundry list of things here include the technological innovations that might be most important to cost-effectively eliminating CO2 emissions from our global energy system, how land will be used in the future. We have a lot of competing demands between agriculture, nature, energy, maybe even carbon management at large scales. So that's going to be a challenge. Can we make better and more detailed estimates of climate change impacts at the national and global scales? There's been a lot of progress in recent years with sort of empirical analyses, but can we be better? How will the food system respond to climate change? There's a lot of work on sort of mitigating climate change. There's a paucity, I would say, of research that's really digging into the weeds of how systems might actually adapt, or will they have to migrate, and what are the consequences? How concerned should we be about environmentally related human health risks, things like antibiotic resistance and emerging infectious diseases? And finally, how could we evaluate and test the stability of economic systems to different combinations of stresses? So these are kind of the ones I carry around lately. And I'll give you a few examples from my work just so you know what kind of research I do. This is from a study that some co-authors and I published a couple years ago now. And everyone knows that cement is a big source of CO2 emissions. It's about 8% of global emissions, and half of that, so 4%, is not related to the burning of fossil fuels. It's actually the process of making cement. You heat up limestone, you drive off CO2, and you're left with the lime. So this is a picture of what those processed cement emissions have done since 1930. This is globally, and you can see it's sort of increasing exponentially. What folks in the engineering community understood, but no one in the carbon cycle community had really ever bothered to calculate, is there's a reverse process by which the cement actually absorbs ambient CO2 from the atmosphere, and it's called carbonation. So folks knew about that because it actually weakens the structures over time. It's why we have to replace bridges and whatnot, but no one had calculated it on a global scale. So we did that, and we basically found that in recent years, close to half of the CO2 from the process is actually being reabsorbed by cements. So I'm going to show one more example, just I'm already running late on time, but another one that really goes from human activity all the way to human impacts. Air pollution kills people, but it's not just in one region. It can also blow into other regions and kill people there. But we actually did a study recently where we looked at where stuff is being consumed around the world. And when you buy something at Walmart, it might have been made in China, pollution was created in China, and maybe that pollution blew out of China and killed someone in a third region. So by pairing a bunch of models together, we were able to create maps like this that show the emissions that are produced in the US kill people all over the world when the pollution blows around. But actually the goods that are consumed in the US actually kill quite a few more people around the world just because we are net importers of goods and services. So by pairing all these models, we could play games with the economic impacts of actually this air pollution and how it's killing people around the world. So this is the kind of stuff that I like to do. Thanks.
I'm going to butcher your name. So you introduced yourself as Phillips. Azebobor Phillips Izebeokai. Is that even close? It'll do for now, right? Thank you.
Good afternoon, everyone. My name is Philip Izebeokai. Most of the things I do is near-surface characterization, particularly for environmental and engineering applications. In characterizing in geophysical characterization of the near surface, basically we are attempting to reconstruct the subsurface from observed geophysical data. And this problem is an inverse problem, which is inherently non-unique. Because of the non-uniqueness of the problem, the inverse models are usually unstable, and there is no unique solution for the problem. Therefore, you may not rely on the models that are obtained. So usually, generally, we are either looking at a 1D problem, 2D, or a 3D problem. And geoelectrical resistivity is one of the most common geophysical methods that is used in near-surface characterization. And 2D and 3D are particularly very useful, particularly in areas where you have complex geological problems. So these are some of the common arrays that have been used over the years in geoelectrical resistivity characterization. So in deciding which array you use, this may depend on the objective of the problem, the geology of the areas, the sensitivity of the array, and many others. Like as mentioned before, the solution is usually unstable, and the models are usually not unique. So because of this, the resolution decreases with depth. So how do we decide, how would we determine whether the anomaly you are seeing is real, whether it is geologically realistic or not? For us to do this, one of the techniques that have been used for some time now is depth of investigation index. And for depth of investigation index, you carry out 2 inversions using 2 different reference models. This is the equations that you may use to determine the depth of investigation. And in doing this, you scale the model. Because you are using 2 different reference models, usually you may choose a model that is, one of the models may be 0.1 times the average resistivity, while the other is 10. So this way, if the models are, if it is real, the index will be close to 0. But if the anomaly is so realistic, the index that you'll be obtaining will be close to 1. As an example, this is just to illustrate what we are talking about. We assume this to be a target object, maybe the buried channel. It could as well be a tunnel, for example. If it's a tunnel, the anomaly will be a high resistivity, but they are basically the same. Now we're trying to determine trying to calculate the syntactic apparent resistivity for that particular structure, and they will equally determine the index model. This is what we obtain, for example, for different arrays. Now you see we did 2 different techniques. This one is smoothness constraint evacuation, even though it's able to isolate the anomaly. This one is called robust evacuation. Again, it's equally able to isolate the anomaly for dipole-dipole array. But by the time we carry out the depth of investigation model, we can see that the anomaly is only at the center about maybe 25 meters depth, and it decreases as you go towards the edge, which means this anomaly here are not geologically realistic, so we cannot rely on them. So the same goes to all the arrays that we also investigated. This one is called multiple gradient array. Again, one of the essence why you do this is for you to be able to select which particular array will be able to image your target object. For this, you can see that the depth of investigation model is more or less uniform. That means if for this particular target, multiple gradient array would be a better option to use compared to the first one we saw, which is dipole-dipole array. The same goes for all the other one. So in the nearest future, we expect to see a situation where the different arrays can be integrated in one model so that you can minimize the errors that are associated with this model. Also, we equally expect to see a situation whereby we can use machine learning in doing the inversion, and again in data collection we expect to see more of wireless sensors being deployed. Instead of going to the field and spend hours in collecting data, you can do that right from your laboratory. Thank you.
Frederick Quattara from the Université de Norbert Zongo in Burkina Faso.
Good afternoon, everybody. Thank you. I want to talk about solar event impacts on the ionosphere because in my country, climate change is important for us, and so it is able to track this climate change by using ionosphere long-term trend study. And also, we found that our model can't model well our data in our sector, so we try to see what can be the solar events that are able to track by our model. After the introduction, I will show some results and discussion and going to conclusion. It's well known that there are 4 types of geomagnetic activity and that are able to introduce ionosphere storms. And so there are 2 possibilities to study ionosphere storm: by using a case study or by using statistical data. In this study, we use pixel diagram. This is the model, the method of Lagrange-Simon, and this model shows that it is able to target CMA's action date in 1950%. I show here an example pixel diagram that show the 4 types of disturbed activity and quiet activity. This is the year of 1994. Here I show an occurrence of geometric activity through season, left panel, and right panel through solar cycle phases. It shows here that each type of geometric activity acts differently through geomagnetic cycle. And it's important to show that here the maximum of shock activity occurs in maximum solar cycle phase. This is well known. And the fluctuating activity is shown in decreasing phases. And through season, the shock activity is more important during autumn season, and fluctuating activity is important for during spring season. This highlights that it's important when you want to target each type of geometric activity to choose where we have many occurrence of this type of activity. Now we show the impact in ionosphere critical frequency of F2 layer. The analysis is shown according to, I don't know. Yeah. Don't see. Okay. Each result is shown by reference of quiet days profile and also the amplitude of frequency value. And if you saw, we can remark that during recurrent activity, during increasing phases, there is no recurrent activity. And all disturbance curves shows nighttime peaks, and by electrodynamic point of view, this can express the signature of reversal electric field. And at daytime, with respect of daytime value, each disturbed action is super than quiet time value. We show that we have positive storm effect by the disturbance activity. Here you show a seasonal variation of disturbance activity and quiet time through season. It can be returned that there are no recurrent activity during autumn, and we show also positive storm effect by disturbed activities. And the important thing is to understand is that in our sector, positive storm effect is seen, and it is important to treat each type of geometric activity instead of seeing the global action of them. And there is no recurrent activity during increasing fires and autumn season. Merci beaucoup pour votre attention. Je parle en français maintenant.
Kyle? There you are. Kyle Frankel Davis from Columbia University, New York. Thanks. Thank you.
All right, so I'm going to take a little bit of a turn towards the science policy interface, and I'm going to highlight an example of some research that I've been doing, looking at trying to develop some transdisciplinary approaches to understand food system sustainability, but also to make a broader statement about a need for considering multiple objectives and multiple outcomes when we're thinking about policy relevant science. So the example I'm presenting here is looking at grain production in India over the past 50 years. And in the panel on the left, you can see that grain production has approximately tripled over the past half century, and that's largely attributable to increases in rice and wheat. And because production and consumption are so tightly linked within India, this has also had important implications for the nutritional quality of Indian diets. So if you look at the panel on the right, you can see that there's been this substantial decrease in per capita iron supply in the average Indian diet as these alternative grains, maize, pearl millet, finger millet, and sorghum have dropped out of the production basket. So a big reason for that is the public distribution system within India. And this is a national program that provides farmers with guaranteed minimum prices for the rice and wheat that they produce. And on the consumption side, it provides highly subsidized market prices to low-income households that are purchasing that rice and wheat. So it's conceivable that by including some of these alternative grains in that same government system, and these are alternative grains that tend to be more resource use efficient and also have a higher nutritional content. If you include those in this same system, you could potentially start to reverse some of these undesirable trends in terms of nutritional outcomes or adverse environmental impacts. So with that in mind, I'm working with a group of researchers at Columbia University and at the Indian School of Business in Hyderabad to answer the question, can increased alternative cereal production improve the nutritional supply of food? Can it help to reduce the environmental impacts of grain production and enhance the climate resilience of food production systems? So I've done some optimizations where I've reallocated harvested areas to different grains where I have the objective of maximizing national protein supply, maximizing iron supply, minimizing water demand, minimizing greenhouse gas emissions, minimizing energy use, and maximizing resilience, all separately, with the constraint that harvested area can only be allocated to crops that are currently grown within a particular district and that calorie production is largely maintained. So this was done at the district level, but I'll skip over this. But when I summarize the results of these optimizations at the national level, I can start to look at whether there are co-benefits or trade-offs for a number of different outcomes that may be of interest to policymakers and decision makers. So the panel in the upper left shows the protein supply under each of these different optimization scenarios where each colored wedge corresponds to a different scenario, and the dashed white line corresponds to the current situation. So you can see for protein that for all of the different scenarios that I consider, that there's a slight increase in protein supply. And the same is true for iron, where there's even a more substantial increase in iron supply. And then for energy, greenhouse gases, and water, for all of the different optimization scenarios, we see reductions relative to the current situation, as well as an enhancement in resilience. So for the crops and scenarios that I consider, there are no real hard trade-offs that occur. And then I'm also thinking about ways to visualize this so that it's more readily interpretable to policymakers or people that it might be useful for. So this is showing the fractional change relative to the current situation for all of the different dimensions that I considered here. And you can see for iron and protein, those axes, the values increase as you move up. And for all of the other outcomes, the values increase as you move down, so that the higher particular scenario line crosses a particular axis, the more beneficial it is for that particular outcome. So if you look at the green line, which is maximizing resilience, you can see that it does a really good job in terms of enhancing resilience relative to the other scenarios. But when you look at the improvements that it offers in terms of greenhouse gases, energy, iron, and protein, it doesn't perform nearly as well compared to the other scenarios. So presenting this information together can allow a decision maker to examine which outcomes and which trade-offs are acceptable for them and the people that they represent, and you can readily incorporate other dimensions that might be of interest locally. So with that, there's more broadly a need to consider multiple objectives and multiple outcomes in tandem, especially when we're doing policy-relevant science. There's also a need to work closely with stakeholders to understand the trade-offs that are acceptable to them and to tailor potential interventions to local needs and local priorities. And finally, to convey that information in a way that's usable and interpretable for policymakers and decision makers. So thanks.
Okay, can we get the speakers to come up, and we might not have enough chairs, but I'll stand and we can have the panel. Is that all right? There's 8 of us, so it's going to be a little crowded. We can take those off. I don't know how to turn them off, though.
You can show the makeup.
Is there a way to black out the screens? This is a little awkward. We've got 8 speakers and 3 chairs. So initially, when we were thinking about this session only a few weeks ago, we asked the speakers to consider a couple of questions, and many of them they've already addressed. What advances in science and technology might we expect in the coming decade that could be transformative? Also, how do you perceive your own role in either the discovery or the implementation of such advances? And then another couple of questions. What do you perceive as serious gaps in your own discipline? And how could your discipline recalibrate or integrate with other fields to better address unanswered, anticipated, fundamental questions or emerging societal issues? And I mean, that was a lot. And I want this conversation to kind of go back and forth, free-ranging, and basically anything is fair game. And I don't want to just ask you questions or have the 3 chairs ask you questions, but I also want you to talk to each other. I'll give you an idea about it. I work for the U.S. Geological Survey and been leading an effort to look at grand challenges in integrated USGS science. And I remember one of the initial conversations was me making the observation to a geophysicist friend of mine that in essence many of the things that we do across disciplines is try to estimate values where we don't have data. And so the reality is that points to kind of a hackathon of what we each do, which is not done as often as I like or many people would like. I think sometimes we fail in that interdisciplinarity. So you guys want to start with the sort of the space science geophysics questions?
Okay. Okay. Thank you for coming. But I wanted to ask for space science speakers. I think Drew and Frederick. I've been getting this question for so many times, and that is the application of space science for the general society. And we know that everything is coming from space, but somebody has a satellite in the magnetosphere, somebody has in the ionosphere, somebody has thermosphere, and they are working independently. But whether we like it or not, they are connected each other. So what do you think about the application of the space phenomena and what the next generation would do, or what is lacking to understand the whole mechanism? I mean, to integrate it into practical application.
Do you want to start, Frederick?
Thank you for your question. I think that according to our position, we are sub-Saharan a country, and we see always the impact of climate change. And we notice that by using ionosphere long-term trend study, we are able to see what's the impact of climate change, and also to see how is the variation of motion in Africa country. And using geospace science, we are able to see what can be done and to prevent catastrophe, and also to secure and have better life for our population. This is why it is important for us to do space science.
Okay. You want to add?
So I guess 2 points on this. In terms of the practical aspects of our science, I mentioned the space weather aspect a little bit, just briefly in my talk. But as we become more and more dependent on satellite technology, this space weather aspect is becoming much more and more relevant to us as a society. And for our communities, the, say, ionospheric, magnetospheric, and heliospheric communities coming together and ensuring that the data from each of our regions are brought together and actually ingested, I'd say, into data assimilative models is probably one of the things that we need to improve upon and continue pushing for from all three communities, and really start getting to more of a system that's more akin to what we do with terrestrial weather, right? Where you have a lot of weather stations all over the planet and these very large climate models that are run, which ingest data from those various observatories. There are some groups that are doing that kind of piecewise with space weather topics and space weather models, but I think approaching a much more global model with as much data as we can get into it is one of the big things we need to do. And then to go even grander in terms of practicality, looking at human spaceflight and our exploration of the solar system, a big challenge that is not often mentioned there is radiation hazard to the astronauts, and how a trip to Mars is potentially insured one way, if you even make it there, depending on the solar activity, because the radiation dose along the way is going to be near, well, bad. It's going to be very bad. So that aspect and basically working towards improved shielding and how we can actually keep those astronauts safe on their journey is another key aspect that I think our community can help with. I don't know if that touched on your question or not. But.
Oh yeah, you did. You did. I will give the audience, if they wanted to add on this point or have any similar burning question. Just instead of just asking.
Is there a question from the audience?
Yes, please.
We have a question from the online audience, and this was for Walter. If less water will be stored in the Asian high mountain regions going forward, where will the water go instead?
Sorry, can you repeat the question one more time?
Yeah. You had mentioned in your talk that there would be less water stored in the Asian high mountain regions going forward. So the question is, where would this water go instead?
Yeah, I think if the glaciers are melting and that reservoir is being depleted, eventually it will either evaporate on its way to the ocean or it will end up in the ocean. So in a way, there are many studies on this. The retreat and the melting of the mountain glaciers will actually lead also to contribute to the sea level rise.
Yes, please.
This is a question for Carolyn. I think you set a pretty high bar for attribution studies in sense of understanding a physical mechanism, having a good long data record, and having a numerical model to duplicate it. I mean, can you imagine having enough data and perhaps seeing a change, but if we don't have an adequate understanding of the process, maybe we see it through artificial intelligence or something, but we haven't connected all the dots yet. Is there any way to make statements about attribution if we're lacking that basic physical understanding?
I think there have been recent advances in event attribution in regard to particular events and to more broad events. So with particular events, I mean any one particular extreme event. For the longest time, we were thinking that our understanding was no single event could be attributed, for example, to anthropogenic climate change. However, recent advances both in the process understanding and in numerical model simulations and also in improved longer data records mean that along those three lines of evidence, we have a better handle on attributing particular events to, for example, climate change. The improving models with finer resolution, more capabilities to have larger ensemble sizes, finer resolution, I think are all contributing towards that. I think we need to make progress along all three data fronts, the models, the observational records, and the process understanding. The challenge with the data is that we can't really go back and collect data that we haven't collected yet. So the length of the record is really a limitation. However, there are advances now that we're going back to, say, historical archives and are collecting data from records that we weren't aware of in previous times. Or we're going back and looking at the paleo record where environmental proxies, records that are recorded in tree rings, stalagmites, marine sediments. We are exploring new opportunities for providing us with longer records to be able to put present conditions in a much longer term context.
Please. I wanted to weigh in at that moment because I'm old enough that for me, event attribution is revolutionary. 30, 40 years ago, we'd never be talking about it. And climate event attribution, extreme event attribution, whether it's hurricanes or droughts, is difficult enough. But I think where we're headed is attribution of socioeconomic phenomena linked to those things, which is pretty scary. I was working and actually teaching in Chile in 2016 when this amazing red tide occurred on the southwest coast of South America. And it was a battle. I mean, I'm not an oceanographer or marine biologist, and I was getting calls from our embassy to kind of help out because there was a huge fight breaking out with people pointing fingers, particularly at the salmon farming industry. And yet it looks like it was a natural event that might have been caused partly by climate change. Stephen, I've followed your work. The world is teleconnected, not just climatically, but also ecologically and socioeconomically. And so we're going to be looking at attribution in lots of different ways, right? Where are the sources? Where are the causes in terms of geography of phenomena that we see where, the Amazon basin is being deforested and is causing precipitation in the Middle East to reduce. But this is a really complicated but exciting field that has to do with the questions about not just physical but also ecological and socioeconomic teleconnections that will very much involve attribution.
Yeah, I completely agree with that, Julio. That's the sort of thing that excites me. It sort of ties what Caroline's doing to some of the human systems that I'm interested in. I actually saw a poster yesterday by a woman named Jessica Gephardt on the Chilean red tide event and the salmon fishery there, and she had estimated the nutrient impacts downstream in other countries from that red tide event. So to your point, exactly, this is the sort of thing we're getting towards. One of the slides I skipped over in my haste was looking at the probabilistic analysis we did. If summer temperatures in India increase by half a degree, how much does that increase the likelihood of mass mortality in heat wave events? And we found it's a very substantial increase in the likelihood. And so if Caroline tells me that that can be pinpointed to climate change, then we could actually kind of close the loop entirely, which would be powerful and maybe make some compelling case for mitigation.
Caroline, do you want to?
So yeah, I think in that context, what was just mentioned, the changes in likelihood, I think that is something in particular also in event attribution that we should always consider, that we're talking about changes in likelihood, loaded dice, and it's not that one event is definite, but we're talking about a range of possibilities. And so with improved computational resources, now these large ensembles and large data sets that we need to talk about these very rare events, in particular when we're talking about extreme events, heat waves, for example, they are becoming more and more available and quicker. So with distributed computing, for example, weather at home is one of those examples where you can run a climate model basically on your home computer, and more and more specific events are being analyzed pretty much in real time or very shortly after real time, and being able to attribute to specific causes. And so I think that is going to revolutionize how we're thinking about event attribution in the near future.
You have a question?
Okay, my question has to do with the issue of data gaps. And in order for us to improve our climate models or hydrologic models, we need data. And I'm always amazed when I sit in these meetings and I see this map of the world projected, and there's one continent that never seems to have data. And so my question for all of you is, why do we have that data gap in Africa? And what can you do in your own respects to be able to fill in that data gap so we can have much more comprehensive either climate models or ocean acidification models?
Thank you. That was actually my question too.
So anybody could.
Anybody else?
So, yeah, I mean, there are a host of reasons why there are data gaps in Africa, and it comes down to differences in governance, the lack thereof, or the lack of long-term monitoring stations. But I think ultimately it gets to Stephen's point that he made in his presentation, that there's a need to get creative in the ways that we collect data or the ways that we develop data sets. And a lot of the presenters touched on it. I think remote sensing is one really promising way to start getting at that. Especially from my work in agriculture, I think satellites really offer a great way to, especially in places where there might not be data that's regularly collected, to kind of sidestep that and for scientists to take control of that and collect the data on their own and work with governments and local communities to understand what the data priorities are, and to develop those data sets kind of in tandem.
Thank you. First, I want to agree with him, but in addition to what he has said, it's not only remote sensing that we need. I think we also need to first develop capacity in Africa. Actually, it's not only in climate change, it cuts across virtually every aspect of Africa. We need, not much is happening. The researchers first need to be encouraged to do more. And for those of us who are in the developed world, you also need to maybe collaborate more with African researchers. In the process, they will develop capacity, they will know what to do, and they will know how to go about it. I think that is crucial, even though the government are not doing much, but the researchers themselves need to be encouraged to do more.
Yeah.
Philip, I completely agree with you. That's the point that I was wanting to make. So I'm just going to basically be seconding your case there, is we need to be promoting partnerships with colleagues and institutions in Africa. So I think that's on us to, I mean, Ndawaki, you should really be answering this question because you do that.
Yeah, I know, but I wanted you to comment on it. Yeah.
And so I think what we need to do is take your model, what you've been doing with your own research and the partnerships that you've developed in Africa. You identify in our own fields what those gaps are and how we'd like to fill them, and then encourage and seek out, I guess, partners in Africa to work with to set up those facilities and those observatories. But yeah, again, so we need to learn more about what you're doing and how you do it, and I think replicate that in each of our fields. But the partnerships are key.
Yeah, I'll comment at the end, but I let the others also to comment on it. Yeah, you raise your hand. Go ahead.
Yeah, but I think another important aspect is that we have to be creative, and we should not wait until the system has changed. And I think for Africa, one good example that I know of, and that I also try now to implement a bit in the region where I'm working, is the TAMO initiative. I don't know if you know that. It's the Trans-Africa Hydrometeorological Observatory, and I think it's an initiative started by John Selker and Nick van der Giezen. So what they do is you have very low-cost weather stations which have very low maintenance, and they have set up a foundation, and their ambition is to have 50,000 of those stations in Africa. So what they do is they work a lot with schools, so they have this schools to schools program. So each school is given one of these small meteorological stations, and there's a very nice web portal. The data is automatically uploaded, there are education materials, and with these kind of networks, I think has a lot of potential just to include the availability, or to increase the availability of data, but also to increase the capacity, and you start at the youngest group of people, which is the next generation who should really pick this up.
Yes, please.
Yeah, I agree with a lot of what's being said here. We had a meeting this summer in Europe. We brought about 40 energy experts to talk about energy development in a carbon-constrained world, and about half of the folks that came were from Africa. And I think there's a few things that haven't been said. One is Africa is not a country, and there's a lot of diversity among the countries of Africa, in particular even with energy resources and infrastructure and capacity. So I think it's important that we actually recognize that landscape there, and that each country has its own set of challenges. I'd also second what Kyle said. There's some exciting data gathering that's going on, both remote sensing, which has come up a lot, and the machine learning to analyze that data, but other opportunistic data sets. One of the colleagues that came to that meeting is using cellular phone records to look for power outages. When you see an entire region not charging their cell phone, you know there's been a power outage. And so you can be clever about this and get data that you might not otherwise be able to get that's not being collected. So.
Yeah, okay, since Drew asked me to comment, yes, we have been doing this since 2007. That's where we start the ball rolling. And in 2007, there was only, I'm speaking about this geospace instrument, small-scale instrument. There was a handful, very few instruments were there. But now we have substantial coverage in collaboration with Tectonic group, a Space Weather group, and we put a lot of instrument on it. But that's not easy to do it. As you said, Africa is not a country. If I ask how many countries are in Africa, I'm sure many people doesn't know about 54. It. There is 54. You are smart. Okay. There are 54 countries there. That means there are 54 different kinds of problems. Mm-hmm. So, and then the most important problem which the scientists in our level cannot solve is two. And that is power fluctuation, power outage, and then internet connectivity. Those scientists, I can make a deal or collaboration with my counterpart, which is scientists. And they are very keen to help each other. We don't pay them. We give them an instrument. They take care of the instrument. When we publish the paper, we add their name as a co-author. And they took that one for promotion. So everybody is happy on that side. The problem is they cannot solve the power issue. That is the biggest issue in Africa we have. And they cannot solve the internet. The internet, we can actually survive. The power issue is if I have an instrument there sitting there recording nothing. So as you say, you can check it with cell phone network or something, but there is a huge problem is power outage right now. So this is not solved by the scientists itself. I have seen several young scientists, political leadership, blah, blah. I would like to have at least, a young generation for science, right, or whatever it is. So, you need to have a generation of young scientists and senior professors. They wanted to go to their country, which is, I'm focusing for the African scientists, go to the politician and convince them that this power issue needs to be solved. There's a lot of ways it can be solved. Solar panel is a very simple way to do it, but they don't have money for the scientists. So this is the starting point that we have in Africa. Not only in Africa. If you go to Far East, the East Asian countries that I have instruments, there's also similar, but I mean, it's not as bad as African.
I would add to that, it's not just on land where we're facing that problem, but actually also in the oceans. I work a lot in the Indian Ocean, and that is an area that is always cited as one of the most data-sparse regions, in particular when you're looking at all the tropical ocean basins. And that has partially to do with less affluent countries in the surrounding areas. It's also an area where shipping routes haven't been as common for very long time periods as, say, over the North Atlantic. And so I think those problems that we've been discussing over the land areas are compounded in the ocean, also because it's more difficult to observe for technological reasons. But I think the capacity development also goes beyond just the land areas, but actually also the surrounding oceans.
Yes, go ahead. A quick point that actually applies to the connectivity aspect of this. So future forward thinking. We're looking at multiple companies now that will be competing to provide broadband worldwide coverage for the internet from satellites, right? These low Earth orbiting platforms, small sats. I think SpaceX wants to put up 12,000 CubeSats basically to provide this broadband internet worldwide, which will at least help with collection of data, say from the middle of the Indian Ocean, as well as regions in anywhere in the world in which internet connectivity might not be readily available. So looking forward, I think that part at least, that we have a bright future, because we should be able to at least get to the data once it's taken.
Yeah, there is a big string attached on it. There is a price tag on that satellite link, so somebody has to pay for it.
According to energy, I think that now it's changed in West Africa. We are doing programs with ECOWAS to see how to solve this problem, energy problems now.
Talk closer to the microphone.
In my country, it is possible now to have solar panel free of charge. And so in a village, each person can have solar panel and use it at home, and to charge cell phone, to use to have light, to study also. It's change now for solar for energy problem now. It's change now. It's a move, but it's not so quick like you want, but I think it is move now. It is important to encourage political program to see what we can do to go very quickly, because you need to go quickly now.
Actually, this is a question for Isaac, but also for everyone else. Again, I have to dial 9 to get out. I'm a federal scientist. And one of the trends that I've been seeing in my 40 years of working for a federal science agency is a move away from process-based science. And I'm extremely concerned because, frankly, we've increased the ability to scale up observations and talk about the world in a very big way, oftentimes without understanding basic processes. And, well, Eric, Isaac, you can take it away from there.
Yes, listen, maybe I'll make a comment about the Africa conversation, then get into that. I'm a Brazilian, and I collaborate with Brazilians all the time. Even though I work in Australia, it's very hard for me to travel to Brazil. But, sometimes part of the challenge to work in those countries, Brazil or Africa, is that the incentives in the academic system, they don't really reward, academics collaborating and working those challenging situations. So if I'm gonna go to Brazil and I wanna get a lovely data set to publish in an AGU journal, it's much more effort than staying back in Australia and getting the same data sets. In a way, the AGU does a pretty good job at encouraging that sort of cross collaboration among the countries. But I think you know, maybe that's not as strong as it should be in academic culture, you know, the rewards for people willing to go to those places. Now, Julio, back to your comments about process, and yeah, I think that's my profile. That's what I do. You know, I get data in the field. I love getting dirty. You know, many of you guys here, you know, you work with global data sets based on satellites or computers and data other people collect. And I love the concept of getting dirty myself and going there and getting the data. And I think, you know, to me, what makes me love that is that I develop a connection and a respect for the data I'm going to produce and for the location, the people I'm working with. We develop a different level of intimacy, you know, with your collaborators when you're out there collecting data, sometimes sleeping deprived or sharing a boat or a house, you know, in the bush. So I think, you know, as you develop those technologies like drones and satellites, it's, you know, there is a high risk that we disconnect from the objectives we're, you know, the objects we're studying. And I think that's not good for science. So I think it's quite important to have that balance between being able to distance ourselves, but at the same time connect to our discipline.
Okay, hold on a minute. Go ahead, please.
Sure, thank you. Brooks Hansen had to step out to another session, but he left me with a question for each of you, which is, as you know, sitting from your position early in your career, what's the one thing you need to advance your science? And the answer can't be money.
Anyone can answer that question? Oh, yeah. Anyone, I'll see.
Maybe I'll follow on that. I think one of my biggest challenges, other than money, are probably disciplinary boundaries. You know, I think we have been trained. I had my PhD in the US, and you know, in the last several decades, we have been going deeper and deeper, you know, into problems, and we have become hyper-specialized, right? I think, you know, having the ability to think broadly is actually quite important, and having people who think broadly, who can talk to you. So I think that would be one of the, you know, the needs and the challenges I would have to be able to develop the things I want to develop is have a bigger cohort of, you know, broader thinkers.
Anyone would like to comment?
I can say. So in space sciences, compared to a lot of science on Earth, we're very much data starved because of accessibility, right? It's not as easy to get a satellite into orbit, particularly considering the scale sizes of the systems we're talking about, and getting global coverage with multiple points basically is a dream. It's something where we're looking forward to approaching, and that's why this miniaturization of technology and capabilities that we now have with small sats are so important for our field. So that would be the answer from my perspective, is more multi-point capabilities and large data sets. Data coverage, I guess is the way to put it.
Anyone else?
From my point of view, I love interdisciplinary research. I think it's the most challenging, but it's also the most rewarding to work on. And so having very diverse sets of people to work with and teams to work with, lots of different disciplines interacting. And so I think as a community, we want to have as diverse and different viewpoints to tackle a problem. And so I think we will always be data limited. More data is always better, better computers, faster computers, more observations. But I think it's really we've heard that in several talks, you need to ask the right questions and come up with smart and clever ideas. And I think only a great group of people can do that. And so having the educated, diverse community that is willing and open-minded to tackle lots of different questions, I think is key.
Yeah, I'll just join the chorus about breadth over depth. I think it's been more than a couple decades, like Isaac said. It's been a couple hundred years that science has been about reductionism, looking at ever smaller and smaller or maybe more remote things. And really what my field is all about now is stepping back from that and trying to look at the interactions of component processes and trying to grapple with the entire system of a human and natural interaction. So I think that's a challenge. I think even AGU, for instance, we all declare our sections, right? Or our departments. We're all hired into a department. And these labels are pretty important, and many of the times reviewers or senior scientists evaluate you in terms of your depth of knowledge in one area. I think we need to move away from that, push back, and the new generation should be rewarded for having breadth, knowing something about geophysics and economics, for instance. And I think that's going to be a big advantage going forward.
Can I actually comment?
Sure.
Steve, you had it in your talk, actually, where you're saying, you know, we walk around with our 20 questions in our head, and we'll speak to other scientists, and then we're always thinking, okay, how do I apply that to my questions, right? And I don't have an answer for how we do this, but AGU is a perfect forum to get people from a variety, right, this interdisciplinary, variety of different fields, hopefully outside of the color of our lanyard, right, into a room and talking about the techniques themselves and the algorithms and the approaches themselves, and focusing on that much more so than the, say, scientific results, right? Because I think we do have a lot we can learn from each other. I mean, I've picked up just a ton from just your guys' 5-minute talks. And I'm sure there are a lot of parallels in terms of methods we can be using and sharing with each other. So promoting that more, especially, again, different colors of lanyards, that would be fantastic.
By the way, Stephen may actually be one of the most interdisciplinary people on the panel. You started out as a lawyer, right? Yeah.
But you
Kinda
know,
look
just
like a lawyer.
to add a little note on that, I think oftentimes people say interdisciplinary science and they imagine getting an astrophysicist and a bunch of people with their own disciplines in a room to work together. And I think that's great, but we should also encourage people who have exposure to multiple disciplines themselves.
Yeah. Walt?
I think even within disciplines, for example, in geophysics, we may also need to integrate different methods. Most of the earth processes problems are coupled problems. Sometimes, for example, I may be looking at the electrical problems, but there is also heat flow that is equally affecting the electrical signal. So we need to develop models that can couple all of these processes together before, not just cross-discipline, but even within disciplines, we need to look at that as well.
Good point. Walt?
Yeah, no, I really like that breadth over depth statement as well. And I think I know my fellow Mcilwain medalists a bit better since yesterday, so know a bit about their background. But I think for all of us, basically, we are all scientists who do that and who connect different disciplines. So I think that's also proof that this is quite a successful way of operating. And then another point that's totally different that I would like to make, I think is also about the academic system. At least in the Netherlands, you see that, you know, on young scientists who have a lot of potential, their development is basically hampered because of the enormous pressure on them on writing proposals, and everyone needs to be able to do everything. And I think that is also a bit of maybe a bit of change is required there. So I think that hampers the development of, at least I see that around me. The pressure is so large on young researchers to be successful, to get grants, to develop your teaching skills, to do science communication. And I think we also have to be realistic sometimes in what is really humanly achievable for young scientists and give them the room to develop them first as, you know, really specialists in a certain field or in a range of fields. And then those other things will come.
That's a great point. Is there a question? Please stand up and walk to the microphone. Thank you.
Hello, thank you. So I want to ask a general question to all of you, and climate change has been said very many times, so I'll ask about climate change. Now, when you look at all the reports about climate change, you'll find they all mention that poor countries will be affected more, but yet they contribute less to the climate change. And so one of the solutions that is proposed, or that is already said, is to become green, use solar power, use wind power. But if you do long-term analysis, we also know that you cannot run a big mega factory using wind power to generate employment and eliminate poverty from the poor countries. Now, do you think that all countries should adopt the same models in combating climate change?
Stephen?
So this is actually exactly what I wanted to raise earlier when the solar charging of phones and lighting came up. I think that that's obviously a big win for some of these developing countries, but it's also, as you point out, that's not how you're going to get an industrial operation going. You need a pretty large amount, probably centralized source of power with very few outages if you're going to have a meaningful manufacturing sector. And at least looking historically, that's how places really develop economically. So I do think that there's going to be a different model for sort of the first step of electrification and maybe a next step of truly developing an economy. And I think it's going to be a challenge to figure out how to do that without adding carbon to the atmosphere. And it may be that in some of these countries, we don't even worry about the carbon because it's going to be very small in the initial stages. And it's really up to developed countries and emerging places like India and China to curtail emissions.
So I'll just add a point to that. I think in thinking about different countries and how they develop and adapt to and mitigate climate change, I think it's important to think about the trade-offs and benefits that different countries can realize and what that on net means globally. So if we're asking a developing country to utilize clean energy, but that ultimately ends up compromising food security or some other aspect within the country with some dire unintended consequences, I think those types of things are what we need to keep in mind when addressing climate change generally.
Anyone would like to comment or another question? Go ahead.
Thank you. So my question is really more in terms of policy. So the point is, initially I used to think that the gap between our research, advancement in research, and implementation was more in the developing world. But having worked around several continents or several countries in the last 3 years, I still see a disconnect between our research advancement or advancements in research and application of this research, or even policy formulation and implementation. So as new leaders in our fields, I mean, my question would be, what's your thoughts? How could we bridge the gap between us, or between you as people working on new borders, new frontiers, or coming up with new innovations, research, and those sitting out there making policies or implementing policies in our research fields or in our scientific fields or application to real world?
Go for it, Drew.
Okay. I think one way that we could start getting our message out there a bit further into a broader population that can then hopefully filter into towards the policymakers. More indirect route, I guess, is education outreach. That's more of a long-term, possibly, approach, of course, right? Like work through the kids who then become the leaders of tomorrow. But just public outreach and education outreach, I think, are critical to that, to getting our message out there. And if you can stress on these outreach efforts, if you can stress to people that communicating with their policymakers is important, and delivering a message to them, letting them know what they think, that's something here that's very effective actually in this country. Is when people write write an email to their congressperson or call their congressperson and let them know they've got a problem, they are tracking those stats. So the more people we can get to do that within the public sphere, the more of an impact we'll have. So I'm just stressing we should do it through numbers, not as individuals.
I'd like to add to what he has just said. Yesterday, one of the most striking things was that people in journalism were given an award for reporting science, and I think we need to start from that. Most of the times when we write paper, we write for the science community. Those in government may never read that paper, they may never know about it, they may never know about your discovery. So we need more and more hands who are trained in reporting science and communicating science findings to the general public in a language that is easy for them to understand. I think that is key. Then secondly, for the very first time, I think before I came, I was going through the website of AGU, and I saw that it is possible for those who are in America to interact with their legislators. I think that also is very, very critical, is very, very key, because the more they know about what is happening, the more they are likely to make policies that will affect the common man. I think those are some of the ways that we can go. There is one issue that usually disturbs me. For example, I try to look at groundwater as well. I've been to US for a few occasions. You will not see, I am not aware, but I've never seen a house where you have a borehole. But you go to Nigeria, virtually every house has its own borehole. Nobody regulates, nobody gives you license, nobody controls how much water you are withdrawing. Nobody, in some cases, you even withdraw, set up a water factory, as said to your neighbor, and his house may collapse as a result of what you have done, and nobody control of that. So we need to do a lot to ensure that policies are made, and institutions also are strengthened to regulate all of this.
Thank you.
Isaac, do you want to?
Yeah, so we think about outreach and science communication, and I would go back that one of the barriers to have more of that and improving our ability to communicate science is academic culture as well. You know, we have a culture in that, you know, the scientist, the one of us who stands up and is brave enough to change the language, to talk to politicians or to the general community is often, you know, mocked by the peers. We have this deep thinking and we like to write our scientific papers, but you gotta change the language. In a way you have to simplify, always fearing oversimplifying to communicate science. You know, no politicians want to read our papers, unfortunately. So I think we do want to have academic rewards for the people who are willing to actually learn the language of the politicians and the general public.
Well, did you have? Yeah. I did want to address that same question, and that is that our culture as scientists and the reward system are the tails that wag the dog.
Yep.
And for example, a lot of our results we give out in a peer-reviewed publication that from cradle to grave might have taken years to produce. And I think that we have to change that culture and start providing much more intermediate products for policymakers. And you know, I work for a federal agency where everything has to go through peer review, and scientific integrity is foremost. But frankly, we have to find ways around it because people need answers in months, not years. I also wanted to go back to the way that Stephen put the question, is that we all run around, you know, with a series of 15 to 20 questions. And I think sharpening those questions as a community is really critical. I've seen cases where there wasn't a sharpening. It actually became blurred by the time that a community worked on a question. And I want to pose a particular question that I carry around with me all the time. And that is that near-term climatic predictability could be a real possibility. You work on this, Caroline, meaning climate predictability from from months to years. That's fine. The climate community is really moving along, trying to address that. All other communities who are affected by whether or not that's true and can be done are not. And I'll give you the example, and that is that ecologists have very little spatial temporally dynamic data. They don't have the data, the theory, or the models to actually make the ecological forecast based on the climatic predictions. That's the case for the socioeconomic sector as well. This is a huge challenge. We have to look ahead at the possibility that the climate community, it is a revolution, that the climate community might actually, break this nut. And then all of a sudden the rest of us, because we didn't have it, and we just didn't think it was possible, had not prepared for that moment. I think that's hugely important, because communities are going to have to move a lot faster if the rest of us are asked, can you forecast the ecological, physical, or socioeconomic consequences of this near-term climatic predictability? So it's the way that you ask the question that's really important. And I think as a community, we have to learn how to do that better so it resonates, across not only the whole community, but across policymakers. Was there anything else that people wanted to add before we close? I wanted to thank my co-chairs and thank the speakers, and I'm actually in awe of you guys. It's pretty amazing to have looked at your records and then meet you in person and hear you talk. And so I'm really grateful and really hopeful with the new generation of scientists. I think it's really impressive, and I and the co-chairs applaud you. Thank you very much. Thanks everybody for coming.
Pleasure.
Thanks for the audience out there.